All right, 6A, we're going to look at binomial probability distributions. So, to know whether or not something is binomial, there are three things that we're looking for. First is a fixed number of trials. So we decide before we start how many times we're going to do something. So let's say we're going to flip a coin. I'm going to say beforehand, I'm going to flip a coin 10 times. Okay, that means that n would equal 10. And I know before I start that I'm going to flip that coin 10 times no matter what. The second requirement is that there can only be two possible outcomes, success or failure. Okay, so if I flip a coin, let's say that heads is success and tails is failure, right? Sometimes we need to classify things a little bit to make it fit. So like if I'm rolling dice, if I roll two dice, there's lots of different outcomes that are possible because each die has 6 sides. But if I say like rolling an even number is success, then there's only two outcomes. There's an even number or an odd number. So that would be binomial. Okay, and then the third one is the trials are independent and conducted using identical conditions. So P and Q, which is my probability of success and probability of failure, have to be the same for each trial. So if you remember in our probability unit where we talk about doing things with and without replacement, okay, so if I'm flipping a coin, it doesn't matter what happened before the next flip, the odds are still 50-50 of whether I get heads or tails. Okay, if I roll dice, rolling a 2 one time doesn't change what the chances of me rolling a 2 the next time are. Okay, but if we are drawing cards, okay, we have to make sure that is done with replacement so that the probability is the same every time. Otherwise, it cannot be a binomial experiment. So let's look at some examples. Okay, first one, toss a fair coin once. All right, so let's look at our requirements. The number of trials, we're going to toss it one time, so we know that n equals 1. Check. The number of outcomes is 2. If I toss a coin, it can either be heads or tails. Okay, something that you're going to have to be able to identify is what is P, what is the probability of success, what is Q, what's the probability of failure. So let's say we're looking for tails, okay? The probability of getting tails is 0.5, the probability of getting heads is 0.5. Okay, so only two outcomes, and then each flip of the coin is independent, that is true. All right, so this is a binomial experiment. Okay. Look at a second example. We're going to have three multiple choice questions. All right, each question has 4 choices, A, B, C, or D, and we're just going to randomly guess and see if we can get the right answer. Okay, so we'll go through our 3 requirements. Number of trials, n equals 3. We know that there's 3 questions that we're guessing on. Okay, number of outcomes, 2. Even though there's choices A, B, C, D, there's a right answer and a wrong answer. Okay, so there's only 2 outcomes. Either my answer is right or my answer is wrong. All right, the probability of me guessing the correct answer is 0.25, 1 out of 4. And the probability of me guessing the wrong answer is 0.75, 3 out of 4. Okay, and then are each of my guesses independent? Yes, because whether or not I get the first one right has nothing to do with whether or not I get the next one right. So this is a binomial experiment. All right, this time we're going to toss a fair coin 5 times. All right, and I want you to think about whether or not that would be a binomial experiment. All right, so let's go through our checklist here. All right, number of trials, n is equal to 5. Number of outcomes, if I toss a coin, it's either heads or tails. All right, and so my probability of success would be 0.5, and my probability of failure would be 0.5. Okay, and then the last question is independent. Okay, does one toss of the coin affect what can happen on the next one? No, so these are independent, so we meet all 3 conditions, so this is a binomial experiment. All right, now we're going to choose 2 balls from a jar of 5 red and 5 green balls without replacement. In this case, number of trials, we know it's fixed, it's 2, we're picking 2 balls. Okay, number of outcomes, there's 2. All right, we're going to choose either a red ball or a green ball. However, we don't know what P and Q are because they're constantly going to be changing. The first time, the probability of me picking a red ball would be 0.5. But the next time, there's only 4 red balls left and there's 9 total. So now it's 4 out of 9. So the probability is going to change depending on what ball I pick first. So that means these trials are dependent. So this is not a binomial experiment. Okay. Now, here's another common scenario. Toss a fair coin until you get heads. All right, there's 2 outcomes, heads or tails. Flipping a coin is independent, but we don't know how many trials. We could get heads on the first try or the 7th try. We don't know. And if it's not fixed ahead of time before we start, then it is not a binomial experiment. Okay, when we determine that something is a binomial experiment, there are 2 things that we look at, which is the mean and the standard deviation. Okay, so the mean, the formula is, remember this is that symbol that I showed you that stands for mean. The mean is equal to n times p, where n is the number of trials and p is the probability of success. Okay, in a binomial situation, another way to say mean is expected value. How many successes can we expect in this experiment? So if I'm going to flip a coin, let's say 10 times, the mean would be 10 times 0.5, which is equal to 5, which means that I would expect if I flipped a coin 10 times, I would get 5 heads, right? That makes sense. Okay, so you might see the word mean, you might see the word expected. Okay, standard deviation. This square root should go over the whole thing. Okay, so make sure when you write it down in your notes, the square root goes over the whole thing. Okay, so standard deviation is n times p times q, and it's the square root of all of that. Okay, so let's do an example. 12% of U.S. teens aged 14 to 18 have debit cards. In a survey of 500 teenagers, what are the mean and standard deviation? Okay, so mean is n times p. So that's going to be, we have 500 teenagers, and they have a 12% chance of having a credit card. I multiply those 2 together, and I get 60. So in a sample of 500 teenagers, I would expect about 60 of them to have a debit card. Okay, my standard deviation is going to be the square root of n times p times q. All right, so n is 500, p is 0.12, and then q is the probability that someone does not have a debit card. Okay, so if it's 12% that they do, then that means it has to be 88% that they don't, because those 2 numbers have to add up to 100. All right, so then we're going to do that math. And we end up with 7 point, I'll round to 2 decimal places, 7.27. So that is the standard deviation for the number of teens who would answer yes.